All right, in this video, we're going to go over a few concepts about the kinetic molecular theory and then dive into Boyle's law. So let's take a look at this. One of the first things we'll talk about is KMT, the kinetic molecular theory of gases. Just some background about this. Remember that when you think about gases, they are constantly moving. It's not predictable, it's very random, and it's typically in one straight line until a collision takes place. Now, we talked a little bit about attractive forces last week, and although you think about those intermolecular forces, in this case with gases, those forces are not really in play because the high energy has taken place. Collisions are a big part of KMT. The collisions that take place in gases are important. Remember that. In gas particles, basically, it's so low you can't even measure the volume. Very, very low. Low volume. We talked down here about the temperature scales a little bit. We'll get into that. And remember that pressure is because of the fact that there's these collisions with gas molecules that hit the tire. And the tire and your bike tire is going to cause pressure because of that. So let's just kind of look at some questions here to see if we make sense of this. What we have here is the idea in a rigid container. Rigid meaning it's not like a balloon. A rigid container means it's not flexible. How does the pressure change when the temperature changes? Well, think about that. The volume can't change, but the temperature is changing, and those collisions are increasing. So the pressure would actually increase because the particles are moving faster and the collisions. Remember, I said before, collisions are going to be a big part of this. Those collisions cause pressure. In a rigid, the next one, container, how does the pressure change when the sample contains more moles? Now, you think of more moles, that just means you have more of the sample. So because you have more of the sample, you have more stuff, for lack of a better term. And because you have more stuff, there's more collisions. So more particles, more collisions, greater the pressure. And again, if you need to pause this to kind of catch up on this, but just, you don't have to write the questions down and write the answers. Just try to summarize what you're seeing here. In a piston, and a piston is something that would be in an engine of a car, how does the pressure change when the volume decreases? And again, this is the relationship we're going to look at next in Boyle's law. How the pressure changes when the volume decreases. In other words, when the volume decreases, the pressure is actually going to increase because there is less space to move within. So the particles are going to collide with each other, but also with the inside of the piston more. And last but not least, in a balloon, so the balloon's flexible, not like the first example, how does the volume change when the temperature is increased? Well, if that temperature is increasing, there's going to be faster molecules. Those molecules are moving faster, and because they're moving faster, that means we're going to have more collisions. So they're going to spread out. When they're heated, the volume is going to increase. Next, like I said, we're going to look at this idea of Boyle's law. And Boyle's law, of course, is named after this good-looking guy here, a nice wig, Jim Boyle. So what we have here is the volume, pressure on X and Y. And so what we found out with this was, if you look at this, as we increase the volume going down, we did some readings on let's say in a lab, what's actually happening is it's going in, as you go bigger volume, it gets smaller pressure. So this is what we call an inverse relationship. So it actually look like this graph right here. Sorry, let me move that down here. There we go. So you can see here that this graph shows that there's a relationship there that is, come back there, buddy, that is inverse. So it's not directly related. So because of that, we can use this this equation to the right. And this equation right here is really just simple algebra, plug and chug, get it done sort of thing. So let's do one example, and then I'm going to let you work on some examples on a Canvas assignment. Oh, just to kind of reiterate, sorry, I forgot I had the slide that these are inverse related. That's why the slope is going that way. And we're assuming, by the way, because we're talking about pressure and volume, that the mass and the temperature are constant. We're not changing those things. We kind of want to isolate those variables like any good experiment would. Okay, so here we have a Boyle's law problem. And this Boyle law problem tells us that we have a gas occupying 100 milliliters at 150 kilopascals. Now, remember we said atmospheres are kind of the best way to go, and liters are the best way to go, typically speaking. But really, it doesn't matter. You can kind of use whatever units you want. It is going to get a little trickier later, and we'll get into that later. But let's just look at this one here. So let's go to over here on the left. What were we given? Well, right away we got 100 milliliters right in here. So we'll write that in. Our pressure is, now before I get to, when we say 1 and 2, 1 obviously happens first, 2 is second. So when you look at this and you say a gas occupies this right here, we're talking about situation number 1, or situation number 1, as opposed to looking at it as being 2 separate entities. So basically what we're saying is the ones go together. So these two are together. So that's why I put this 150 right here. Find its volume. So we're insinuating that that's a new volume. We do not know what that new volume is, but we do know what the new pressure is, and the new pressure is 200. So that's why we have this this 1 and this 2. And I should have probably talked about that a little more detail, but it makes sense. So how would we do this? Well, we look at this equation right here, and we say, well, we got all these numbers over here. Let's sort of plug and chug here. Now, I'm going to put the units in, but you really don't have to, because it's always going to end up being the units that you started with, and I'll explain that in just a second. So my P1 is 150, I got that right there. My V1 is 100 milliliters, I got that right there. And then my P2 I know to be 200 kilopascals, and I do not know my V2. So again, simple algebra, I'm going to divide both sides by 200 kPAs, 200 kPAs, and that's of course going to cancel this out over here. If I multiply everything, of course the kilopascals are going to cancel out, and that's why I said, you know, you're going to get the milliliters. If you started with milliliters, you're going to end with milliliters, and your answer ends up being 75.0 milliliters. So we simply do the math on this part right here, and we figure out that it's 75.0 milliliters. We'll put that 0.0 in there because of the 3 sig figs that were given here, here, and here. Of course, all the givens had that. So that's really the Boyle's law in a nutshell, and 10 minutes here, we got it done. Go ahead and try the example problems, and when you're done with those, you can move on to the next part of the module.